Okay. Hi, everyone. Welcome to QNLP. So, Tai-Danae Bradley will be talking about unpacking language with reduced densities.
All right. Thanks, Alexis. And thanks for everyone for tuning in, and especially to the organizers for the invitation. So I'd like to describe for you in this talk some joint work I did while at the CUNY Graduate Center. This is joint with Yannis Vlasopoulos at Tunnel in New York City. So you can find this on the archive. This is language modeling with reduced densities. And there are a number of ways that I could introduce the ideas in this paper, but I think out of all of those ways, I'm going to try to start with something that I think is probably familiar to a lot of you who are listening, and that is this great quote by linguist John Firth: "You shall know a word by the company it keeps." So that's this idea, or one way I like to think of this is that if you want to know something about the meaning of a word, then you should look at the network of ways that that word fits into its environment in the language. I think that's kind of the idea behind first quote. This is not unrelated to the distributional hypothesis, where the meanings of words are somehow captured in the context in which they appear. So I want to think about this idea for a little bit. And in particular, here's a visual picture I have in mind when I think about the company of the word, of a word like orange, for example. So on the screen, I have a whole bunch of different expressions that contain the word orange, and then sitting in the middle, here's this word. And the idea is that if you want to understand something about it, then you sort of look at the totality of all of these expressions, or sort of what goes with what and what's captured in this network. I think that's the idea behind first quote, but there's a little more to the story, and that is the statistics or probabilities attached to these expressions. So I can certainly take two words like orange and idea down here, and I can concatenate them to get a phrase like orange idea. But we know that the probability of that phrase being spoken in the English language is quite low, or the statistics of that expression or the frequencies are pretty low. But that also contributes to the meanings. And so what you'd really like to do to understand this word or to understand this picture is to somehow decorate these arrows or this network with something like conditional probabilities, and that will also contribute to the meanings of these phrases. And so that's one thing that our paper is about. We have this network of expressions, and we find a way to incorporate probabilities in a nice principled mathematical way. So that's one thing I want to describe for you later on. But there's a little bit more, right? If I want to do something with this, maybe I have some application in mind. Maybe I want to model this on my computer and I want to probe it or investigate it further. I'd really like to map this structure or this scenario into the space of linear algebra. Now, when I say that, you might have something like vector embeddings in mind. But what I actually want to describe for you, and here's another part of this talk, is a way to take expressions and words, phrases, sentences in English and assign to them matrices or particular linear operators. And here's sort of the nice piece of this assignment. Just like I can take two strings on the left-hand side of the screen and sort of compare them, there's a way, and I'll describe this, to also analogously compare the matrices that are representing them. And just like I can think of incorporating the statistics or decorating my network on the left with probabilities, I'm going to describe for you a way to do an analogous decoration on the right-hand side in the space of linear algebra. And the upshot of the talk and the sort of punchline of the paper that I'm describing is that this passage from essentially sequences of symbols and language with probabilities into the space of linear algebra is compatible with this sort of network picture or these orderings, and it preserves the probabilities in a nice way. So I like this because it's sort of a crystallization or representation of the ideas captured in John Firth's quote. So that's what I want to describe for you in the next few minutes. Sort of the three things that are on the screen. What really is this structure that I'm talking about? I have this network and I have these arrows. What's the mathematics behind that? what exactly is this assignment into the space of linear algebra? And what do I mean that the structure on the left is preserved as I pass to the right? So first things first, let's zoom in to the left-hand side of the screen and understand what's really going on here. So just sort of intuitively, you can see it right here. I have essentially strings of words or sequences, and you'll notice I've drawn an arrow from one expression or one sequence to another if it's contained in that. So, here's ripe orange. There's an arrow from ripe orange to small ripe orange fruit because ripe orange is contained in that as a subsequence. There's no arrow between orange butternut squash and a beautiful orange sunset because neither sequence is contained in the other. So that's the structure. Let's just make this a little bit more formal. So comparing sequences, what's sort of the mathematical way to express this intuitive idea? So let's just start with a finite set. Think of X, this finite set, as the set of your atomic symbols in your language. For this talk, we can just think about X as the set of all English words, for instance. And what we want to do is to consider the subset of all valid sequences of length at most n, right? So pick some maximal length, and now think of all sequences up to that maximal length, valid sequences in English, and we can compare them in exactly the way I just described. So, the sequence I climbed is contained in the sequence I climbed the tall mountain, just as a subsequence containment. Orange sits inside ripe orange, which then sits inside small ripe orange. So you can check that this relation, I'm expressing it by less than or equal. You can check that this is both reflexive and transitive, which succinctly means that it's a pre-order. So, if a pre-order is not familiar, a pre-order is just a partial order without anti-symmetry. So that's the mathematical structure. Sequences form this nice pre-order. I can compare them in this way. All right, but we mentioned that that's not quite all. There's something else we want to incorporate, and that's probabilities. So how do I introduce probabilities into the picture? Well, let's just do it. Suppose that I have a probability distribution, call it pi, on my set of sequences of length n. Now, this is a joint distribution on sequences, so I have everything. In particular, I have conditional probabilities. So what I'd like to do is now let's just imagine decorating each of these containments with the appropriate conditional probability. So what do I mean? Here, we already said that orange sits inside ripe orange. So I want to think of decorating that containment, or I'm sort of witnessing that containment with this number, namely the conditional probability of seeing ripe orange given that orange is there. Okay, so I have that number and I'm just going to sort of stick it on top. But I can do this again, right? Maybe ripe orange sits inside of a longer expression like small ripe orange. And I can again take the conditional probability for that, right? The probability of small given that ripe orange is there. And then I just continue and I decorate this. But here's the nice observation. Because my probabilities are obtained from a joint distribution on sequences in this way, my probabilities actually compose. In other words, if I look at the conditional probability for sort of my small word like orange into this longer expression, small ripe orange, that conditional probability, it turns out, is precisely the product of these two intermediate probabilities. All right, anytime you have a picture like this, I sort of have three things and the arrows compose. This is just shouting out to us that category theory is lurking in the background. Now, I'm not sure whether everyone in the audience is familiar with category theory. So maybe the punchline is just what's on this screen. I'm comparing my sequences by sort of this subsequence containment. I have a joint distribution and I get conditional probabilities and I decorate them in this way and they compose. All of this can be wrapped up in a nice sort of formal mathematical way. That's what's on this screen. There are some words here that I haven't introduced, but let me just sort of say them quickly for those who are familiar with some more categorical ideas. And I just want to mention this to let you know that there's some nice mathematics lurking in the background. So here's kind of pulling back the curtain. I'll say this quickly. It turns out that if you look at the unit interval where our probabilities lie, and you look at the sort of usual ordering on them, usual multiplication of numbers, and the number 1, that data is what's called a symmetric monoidal category or symmetric monoidal preorder. And if we look at our set of sequences, and to every pair of sequence, if we define a number between them in this way, and you work out all the details, all of this intuitive idea that we have, it's sort of succinctly put as it's a category enriched over probabilities over the unit interval. So what you can do, I can take 2 sequences and I can get a number out of them. I'll say, if my little sequence S is contained in my longer sequence S prime, the number I want to associate between them is just this conditional probability, the same one we saw in the previous slide. If these sequences are not comparable, then I'm just going to assign to it 0. So all of this can be made precise in a nice category theoretical way, and it turns out to be enriched category theory. But the idea is just this containment together with decorating. That's the thing to keep in mind. Okay, so that's really the left-hand side of the screen. That's pretty simple. Subsequence containment, and I decorate with probabilities. But maybe, what we really want to talk about, and the meat of all of this, is how do we pass into the space of linear algebra? So I realize this is the quantum NLP workshop. I haven't yet mentioned anything about quantum, but now here it is, or we're getting there. So here's sort of the punchline. What we're going to do is to consider positive semi-definite operators on the free Hilbert space generated by our finite set, our finite alphabet, positive semi-definite operators that are associated to our sequences. Now, you'll remember, we can compare sequences, right? This was a pre-order. Turns out you can also compare positive semi-definite operators. So I think this is a familiar order to a lot of you, the loner order. So what it means is I'm going to say that a positive semi-definite operator rho prime is bigger than, say, rho, if their difference is also positive semi-definite. So whenever I have 2 positive semi-definite operators and I have this less than or equal to sign, that's the loner order. That's what this means. And the sort of punchline is, I'm going to tell you how we get an operator from a sequence, and we'll see that assignment actually is order reversing. So I mentioned category theory earlier. What this means is that we have a functor or a contravariant functor in the background. But before we get there, what exactly is this operator? Given a sequence in language, how do I get a positive semi-definite operator from it? Here's the main idea, the roadmap. It starts with the fact that we have a probability distribution on our set of sequences. This is like the main ingredient. Now here's the outline. Given that probability distribution, we're going to define a particular unit vector in the free Hilbert space generated by our set of sequences. That decomposes as an n-fold tensor product. Now, I have this unit vector, and associated to it is a pure quantum state, a rank 1 density operator, namely orthogonal projection onto this unit vector. Now, I'm going to take a slight modification of the reduced density operators of this pure state. And that slight modification is going to give me operators associated to sequences. So just think, I have a pure quantum state that I've obtained from a classical probability distribution, and the reduced densities of that pure state are going to give me operators associated to expressions in language. That's kind of the roadmap. But now let me tell you, what is this unit vector, and what is this slight variation of reduced densities? Let me tell you that next. The unit vector we consider is very, very simple. I have a whole bunch of sequences of length n. There's a probability distribution attached to them. So I just add up all of my sequences and weight them by the square roots of their probabilities. So the square root just ensures that this is a unit vector. And here the symbol little s, I just mean that's one of my sequences of length n. Now, because I have passed from sets to free vector spaces on those sets, the vector representation of a sequence is just a tensor product of the vectors for the individual words. And those individual words, those vector representations, they're just standard basis vectors, right? So the tensor, the vector for something like, beautiful orange sunset is just beautiful tensor orange tensor sunset. And those individual words, you should just think of them as, standard basis vectors or one-hot encodings, if you like. So at the bottom of the screen, I have what I like to visualize. I like to think of psi as a tensor network diagram or a string diagram. So it's just a node with n edges coming out, since it lies in an n-fold tensor product. Okay, given psi, and given a sequence like, beautiful orange sunset is, how do I get a matrix or an operator from this? Well, take your sequence. Here on the screen, I have a sequence of length n. Compose its vector representation with psi that we defined on the previous screen. Then form projection and trace out the remaining sites. But, I want to leave the rightmost site open. That's because if I have open indices, that guarantees I actually have a linear map or a matrix from, the free space on X to itself. Now I plugged in my word to my sequence to the right, but you could imagine plugging in everywhere and tracing out the remaining sites and see what you get. That's fine. The point is, because this is obtained by the partial trace, I'm going to refer to this as a reduced density operator. It's not quite a density because its trace may be less than 1, but it's certainly positive semi-definite. Now, there are lots of things to observe now that I've done this, so let's just kind of go through them quickly. The first thing to notice is that the partial trace involves a sum over all words preceding the sequence that you plugged in. So in the previous slide, I had a sequence of length 4, but let's just say, suppose the word I'm interested in is orange. So here's the density, the reduced density for the word orange. So I plugged in the word orange and I traced out the remaining sites. But this vertical edge here is just shorthand notation for sum over all of the variables that go in that site. But those variables are precisely words. So what this picture on the top means, is something like orange, the density for it, is the density for ripe orange, plus small orange, plus, things are orange. So the density for orange decomposes as a sum of densities for every expression that ends in that word. So as far as the linear algebra is concerned, orange is the totality of all of these expressions that contain it. So this is nice because I think back to that network that we looked at, that colorful network, and the linear algebra is sort of capturing that nicely. But there's a couple other observations to make. Let me just point out the fact that if I take, for example, the density for ripe orange here, imagine just subtracting that, from both sides. So now I have row orange minus ripe orange. That difference is a sum of positive semi-definite operators. But that's exactly what it means for orange to be larger than ripe orange under the loner order. So you'll remember, I can compare strings and I'll say, okay, orange sits inside ripe orange. And now that I've passed over into the world of linear algebra, that relationship is sort of reversed. So this is, one way that you can see that I have this sort of contravariant mapping from sequences into densities. But there's something else to say. We mentioned the importance of probabilities. So I'd like to attach probabilities into this operator representation, and we haven't seen them yet. But actually, we really have. So I mentioned that these aren't quite true density operators because their trace may not be 1. It turns out you can check that the trace of an operator associated to a sequence is precisely the marginal probability of that sequence. That's not too hard to see, right? Our vector psi is essentially just a bunch of joint probabilities. When I apply the partial trace, I'm essentially summing over all of the variables except for the one I plugged in, but that's precisely the idea of marginalization. So the trace recovers the marginal probability, and I can ask, what is the analogous decomposition for the normalized operators, right? The true density operators that I get after I divide by their trace. When you write this out, you can see that you get the same decomposition, right? Orange is ripe orange plus small orange plus blah, blah. But because I've introduced this factor of marginal probability, you actually get that there are coefficients in this decomposition. And those coefficients turn out to be exactly the conditional probabilities that we talked about before. So this is nice because now I've seen my conditional probabilities appearing in a nice way, but I'd like to make the math a little bit tighter. What I'd really like to do is, it turns out trace 1 densities aren't comparable under the loaner order, so I don't really want to normalize. I just want to decorate with conditional probabilities. And if you sort of write down what this means, you'll see that conditional probabilities on the space of linear algebra compose in the same way that they did with my strings. And so I end up getting the exact same structure. I get a category of density operators enriched over probabilities in this way. So that's sort of a lightning fast tour. The top half of this screen is just saying, hey, this can be made more formal in terms of enriched category theory. The fact that my structure, my sort of partial pre-order structure decorated with probabilities is preserved under this passage into linear algebra. The sort of sophisticated way to say that is, this assignment is what's called an enriched functor between these categories enriched over probabilities. So that's the whirlwind tour of the paper. I just want to quickly say, behind the scenes, all of this rested on our choice of unit vector psi, the sum of everything weighted by probabilities. And you might ask why. So let me just say, in certain cases, the reduced densities of this pure state have nice combinatorial probabilistic interpretations. We just heard a nice talk about formal concept analysis by Sean. Turns out the eigenvectors of these reduced densities are closely related. In a more applied setting, you can look at eigenvectors and eigenvalues of this state. They turn out to be a key ingredient in a tensor network generative model. I'm referring now to joint work with Miles Studenmeyer and John Torilla. And you can even think, beyond natural language, but what about images? Maybe I have sequences of bit strings that form images. There's been analytical work on studying the entanglement properties of this state. That turns out to has a nice low rank tensor network representation as well. So there's a lot packed into this one vector, and I'm just sort of, adding one more thing to the list of what we can do. I like this picture. I see that I'm out of time, so I'll end here.
Thanks a lot for the talk and the beautiful pictures as well. So let's go to the questions. There's maybe one quick question on how do you define the order of subsequences between your strings of words, and the question is, does your order include AC is smaller than ABC? So do the subsequences need to be a whole block inside?
Yeah, right, yes. So I would like, yes, that is AC contained in something like ABC. So for this talk, yes, I would like that. So my subsequence are subsequences of consecutive symbols, yes. Okay. But for future work, certainly we'd like to expand that. Absolutely, yeah.
Thank you. Then there's a second question on, do you have thoughts about how to incorporate semantics? For example, orange is a fruit, or more fuzzy relationships?
I would like to, yeah, orange is a fruit maybe versus something like orange is a color. That seems to depend on sort of the context in which it's used. So if I say I like orange, probably you know I'm referring to the color orange, versus if I say I like an orange fruit, I guess you know. So I think it's very interesting that some of the popular language models that are out there kind of capture that, and all they have are their statistics, right? You just have all of the text on the internet, which really means you sort of have a probability distribution, and somehow that's enough to distinguish between if I use orange, does that mean it's a fruit, or do I mean the color? And so what I'm sort of getting at here is that there's something really interesting that you can infer that just from the probabilities. And so I'd like to understand that mathematics more precisely. And I think of this project as just one step towards getting there. That's certainly a goal.
Thanks. And then there's one question from Ross: does your enriched functor have an adjoint by any chance?
I don't know. I don't know. That's a great question. Of course, that's the question that one always asks when one has a functor. At the moment, I don't quite know. So one thing that's interesting is that this functor is not quite full, in the sense that what am I trying to say? So I think that one can show that, maybe like two sequences that maybe have similar statistics map to the same operator. And so if you want to go in the other direction, maybe things you have to be a little bit more careful. So I don't know about an adjoint yet, but that would be very interesting. And certainly I can look into that. Yeah. Great question.
A hard question for sure.
Yeah.
And then maybe a last question, we have a bit more time, is so are you restricted to standard tensor network methods such as MPSA, MERA, etc., or can this tensor network take the structure of the language tree to have a possibly more intuitive interpretation?
Yes, great question. So the reason that I chose the vector psi, right, this blob, you'll notice this psi does not have a tensor network representation. So I have not written this as a MERA or as an MPS or anything. And that's precisely because I want the flexibility. I exactly want that flexibility to think maybe beyond, outside of the box of the usual tensor networks that are used. Maybe there's something a little bit clever or a little bit different that we have to do. I have baked that in. We've baked that into this because we want that flexibility. So yeah, the question is, what is the right tensor network for language? Absolutely, great question.
Nice. And maybe I can add a personal question on top of that.
Sure. Yeah.
At some point, you mentioned so when you're constructing this this category of all the sequences, you're saying that you want the correct sequences in English, and
yeah,
in the rest of the talk, it's not so much about correctness or grammaticality, and more about likeliness. So in a sense, an orange idea is not incorrect; it's just very unlikely.
right.
And I was wondering if there's any chance you could include more grammatical structure into the model rather than just having sequences. So maybe something linked to the syntax trees that we mentioned just before.
Yeah, maybe. That's a good point. Right. One thing I didn't mention in this talk, and so Alexis, I'm glad you asked that, is that there's been work with the DISCO framework also attaching really positive semi-definite operators to sequences. So one, a natural question is, how are these things related? I think maybe kind of like the sort of punchy way to say maybe the difference in these approaches is that here I'm actually thinking of letting the statistics serve as a proxy for the grammar. So, earlier I mentioned these, big language models that are out there. It's kind of interesting that they can do a lot even without yet knowing about language. Without knowing about grammar. So in this context, I'm kind of thinking, hey, how much can we say? Like, how much can we get away with if you just have the statistics? But certainly later on, yeah, maybe there's a nice way to also incorporate, what does valid mean in particular in the syntax side. Certainly.
Yeah, there's going to be, I think Martha will be talking about DISCO and
Great.
matrices later on this afternoon.
Excellent. I look forward to it.
Yeah, thanks again for the great talk, and let's keep the discussion going on Slack.